Good morning, boys and girls, and welcome back to another day here. More on the derivative and what derivatives tell us today. Okay? Today we're going to be talking about concavity and the second derivative test. So first, I guess we should talk about what concavity is. In math, you might be thinking science-wise. You've talked about how some things are concave and convex. In math, we just deal with concave stuff. A function is either concave up or concave down. I have a function sketched here for us as a quick example, and a function is concave up. Easy way to kind of describe this: it's concave up if it would hold water. If you were to think like if I were to dump water onto this function here, if I were to dump water onto this graph, the places that would gather and hold the water, that is where the function is concave up. So like right in here, that is concave up. Okay, over in here, this is concave up. Right? The places where the water is going to run down and come off, up here the water is going to run down off of this, that is concave down. So that's one of the things we're talking about when we talk about concavity. If it's concave up, I like to think it holds water. If it's concave down, it does not. Okay, so the concave up holds water, concave down doesn't hold water is an informal way of us kind of defining concavity. But obviously we need something more mathematical to define concavity. So if we start looking at the slope of the tangent line, okay? If I start looking at the slope of the tangent line at points, if the slope of the tangent line is decreasing, here I've got a very, a large positive slope, maybe a slope of like, say, 10 or so. But then I move on a little bit, and now I've got a slope of like maybe 7. Move on a little bit, a slope of like 3. On a little bit, slope of 1. Slope of 0. If the slope is decreasing, still on this side, hey, now slope of -1, slope of -2. If the slope is decreasing, getting smaller, then we say it is concave down. And if the slope is increasing, hey, I'm at a slope of like -3 here, I don't know. And then I'm at a slope of -1, slope of 0, slope of 1, slope of 5. If the slope is increasing, then we say it is concave up. All right? So that's our more mathematical way of doing it. And then the slope of the tangent line, I guess we could also just call that the derivative, right? So I'm going to add that to our definition down below here. Okay, so now we have that, a function is concave up if it holds water, or if its derivative, f prime, is increasing. Okay? We have that it is concave down if it doesn't hold water, if f prime is decreasing. Now, I guess then if we're talking about when f prime is increasing or decreasing, we could actually then go back and relate that I know a function is increasing or decreasing if I look at its derivative. So if I look at the derivative of f prime, that would be f double prime. So we can use this idea now to come up, again, this theorem does not have a name, so I'm going to call it theorem 4.6, and I'll put it on the board here in a second. But we can use that idea that if I look at f double prime, that'll tell me when f prime is increasing or decreasing, which will then tell me about the concavity of the function itself. Okay, so this is kind of your second derivative test. Well, it's not officially the second derivative test. We'll get to that in a second. But theorem 4.6 kind of sums up what we were just talking about there. If f double prime is positive, if it's bigger than 0, then I know that f prime is increasing. And if f prime is increasing, then the graph is concave up. So if f double prime is greater than 0, then the graph is concave up. And if f double prime is less than 0, if it's negative, same idea then, that must mean f prime is decreasing, which means f is concave down. So if f double prime is less than 0, then f is going to be concave down. All right? Okay, moving on here. Okay, now our last little bit with this. Points of inflection. A point of inflection is a point where f double prime changes sign. Okay? When f double prime changes sign, that means f is changing from concave up to concave down. And so when we change from concave up to concave down, we call that a point of inflection. And point of inflections are going to occur at the critical points of f double prime. Meaning, again, those same places we looked for critical points in f prime before, when the derivative was 0 or undefined, I'm going to look for those same things in f double prime. All right? So just graphically what it looks like here, like maybe here is a point of inflection. I'm changing from concave down to concave up. Or maybe like right here is a point of inflection. Kind of like that halfway point between these things. Those might be my points of inflection for this function up above, okay? It's where f double prime changes sign, or where f is changing from concave up to concave down. That is a point of inflection, and you will find it by finding the critical values or critical points. All right, so bottom line, today's stuff is a lot like yesterday's stuff, where we are going to be looking at, now instead of the first derivative, the second derivative, and instead of looking whether it's increasing or decreasing, I'm going to talk about the concavity of the function. All right. So if I give you a function f and I ask you, describe the concavity of this function, you would want to take the second derivative. So if I ask about increasing, decreasing, that's first derivative. If I ask about concavity, we are going to look at the second derivative. So to find the second derivative, I first got to find the first derivative. 20x cubed minus 60x squared. And then I'm going to go find the second derivative. F double prime of x would equal 60x squared minus 120x. And again, what I want to do is I want to set this equal to 0, or see where it's undefined. So in this case, just where it equals 0. I can factor out a GCF, maybe in this case a 60x. Draw my line. I get x equals 0 and x equals 2. So again, those are my two critical points, critical values. And so I'm going to do a number line now. Again, I don't really care too much about, what's happening numerically, but I do care about the signs of what's happening. And I'm going to test the different values. If I plugged in a number less than 0, like -7, 60 times -7 would be some negative number. -7 minus 2 is going to be some negative number. A negative times a negative is a positive. All right. So, because the second derivative is negative over here, I know that the function f is going to be concave up. Sorry, since the function is positive here, I think I said negative the first time, I know that the function f is going to be concave up. All right. I'm going to do the same thing. I plug a number between 0 and 2 now, so maybe like 1. If I plug 1 into the front, 60 times 1 is positive. 1 minus 2 is negative, so positive times a negative is a negative. And then 2 onwards, if I plug a number bigger than 2, like 7, 60 times 7 is positive. 7 minus 2 is positive. Positive times a positive is positive. So I know f is concave up on negative infinity to 0 and 2 to infinity. In the last section, we talked about how sometimes those are inclusion versus not included symbols. We talked about how our book is always going to use parentheses. With concavity and the second derivative, these always have to be parentheses. So that's why it might just be good. When we're talking about increasing, decreasing, positive, negative, or concave up, concave down, it's just always going to be parentheses, and I think that'll be the easiest way to make this rule straight. Okay? F is concave down on 0 to 2, okay, because the second derivative was negative. All right, so as you can see, very similar to yesterday's lesson, except we're just now dealing with the second derivative. So I'm going to keep this kind of fairly short and sweet for you, I believe. Oh, and I forgot to do the last part of this problem here. We identified where it's concave up, concave down, but we also needed to identify our points of inflection. So again, points of inflection, POI, occur when the function changes from concave up to concave down. So at 0, there's a point of inflection, and at 2, there's a point of inflection, because that's where we're changing concavity. All right? When you find points of inflection, they are points. We found out where they are located. We said we have one at 0 and one at 2. However, to get the y coordinate of these points, we need to go ahead and we need to plug this back in to the original function. So if I go find f of 0, if I plug 0 in here, I get 0 minus 0 plus 10. So at 0, 10, there'd be a point of inflection. And 2, if I go find f of 2, let's see here. And if we plug into, I get 5 times 2 to the 4th, which is 80 minus 20 times 2 to the third, which is 160, plus 10. I get f of 2 is negative 70. So those would be my points of inflection. Okay? All right. Last little thing here. The second derivative test. Okay? Now this is the official second derivative test, and we will use this by name, so it's good to know the name of what this says. But the second derivative test says that if f primacy equals 0, if you have a critical value, a critical point in your first derivative, okay, and f double primacy is greater than 0, the second derivative is positive, meaning it's concave up. If I've got a critical value and it's concave up, okay, well, that critical value then must come at the, I'm trying to see where to point here. You know, that's got to come at the very bottom of this, so it has to be then a relative minimum value. Okay, if f prime of z is 0 and f double prime is less than 0, so it's concave down, okay, concave down, now that critical value would have to be at the very top, so it would have to be a relative maximum. So sometimes we're not going to be able to show that f prime changes sign from negative to positive or positive to negative to show the existence of a min or a max. Sometimes we're going to have to look at the second derivative and at the concavity. And just know that if we have a critical value and it's concave up or concave down, that's going to be a min or max. Again, I do this with my hand all the time to kind of, remember which one is which. Okay, so for this next one here, it says to locate the critical points of the function f and then use the second derivative test to see whether they're mins or maxes. So again, to find critical points, you're going to take the first derivative and set it equal to 0. I'm going to factor that, or see where it's undefined in this case, just where it equals 0. 4 minus x. So in this case, I get it at x equals 0 and x equals 4, my critical values. All right? So now to see if they're mins or maxes, again, I could do my number line and show that it's changing from increasing to decreasing in this case, but we're not always able to do that. So I'm also now going to go look at the second derivative of this function. F double prime of x is 12 minus 6x. All right? And so now if I plug in these different values, f double prime of 0 is 12 minus 0, or 12. And again, I really don't care about the number. What I care about it is positive. So because at 0 I have a critical value, and because at 0 the second derivative is positive, it's got to be concave up. So at 0, at x equals 0, there is a relative min, or a local min. Okay? If I find f double prime of 4, I get 12 minus 24, or negative 12. And so now, because the second derivative is is negative, I know it is concave down with a critical value, which means at x equals 4, there's a relative max. And I know that by the second derivative test. Okay, that is the second derivative test. Okay, one last little one for funsies here. I'll give you some information about a function we want to sketch ourselves a graph. So I tell you that f prime of x is less than 0, and f double prime of x is greater than 0, from negative infinity to 0. And I tell you that f prime of x is greater than 0, and f double prime of x is greater than 0 on 0 to infinity. All right? So now we've got to think about what that tells me. If f prime of x is less than 0, that means the function is decreasing, right? And if f double prime of x is greater than 0, that means we are concave up. Good. If f double prime of x is greater than 0, we are increasing. And then we already said that f double prime of x greater than 0 means we are concave up. So this is some function that I am decreasing from negative infinity to 0, but I'm concave up. And again, I don't know, I drew it there. It could be crossing anywhere, I guess. It doesn't say it's got to go through the origin. And then from 0 to infinity, it's going to be increasing and concave up. So it's going to kind of look like that. And again, my graph could have been, there. That also works. Decreasing and concave up, increasing and concave up. But you should have something that kind of looks like those. All right. Give this a shot now, boys and girls. If you got questions, come see me.